Chapter 10, the t-test for two independent samples. For this chapter, our learning outcomes or objectives are as follows. First, we'll understand the structure of research study appropriate for independent measures t-test hypothesis. Second, we'll test difference between two populations or two treatments using independent measures t-test. We'll evaluate the magnitude of the observed mean difference, effect size, using Cohen's d, r squared, and/or confidence interval. And finally, we'll understand how to evaluate the assumptions underlying this test and how to adjust calculations when needed. The tools that you will need to be successful with this chapter. First, we'll need to review sample variance. Again, as we know, sample variance is equal to the sum of squared deviations over degrees of freedom. Standard error formulas from Chapter 7. So we know that the standard error is equal to standard deviation of the population over the square root of n. And then information learned in Chapter 9, which includes a single sample t-test process, distribution of t-values, degrees of freedom for a t-test, and estimated standard error. So to begin, we learned that the single sample t-test meant that we take the mean difference and then divide by the estimated standard error of the mean, and the estimated standard error of the mean was equal to our standard deviation over the square root of n, or variance over n, and we take the square root. So all of these things need to be reviewed so that we can build on that information and learn the new technique of testing two independent samples. Before I go any further, what I'd like to do is just review, beginning with Chapter 8, what the structure looked like with the z-test, then Chapter 9, which was an a single sample t-test, and now introduce the elements of Chapter 10, the t-test for independent measures t-test, and speak a little bit briefly about the next chapter, which is the t-test for repeat measures. And again, all of the phrasing for the different t families just has to do with how many samples are we looking at, and what do the participants look like in those samples. Are they the same individuals or are they different individuals? So again, a brief review. Our z-test, right? We conducted a z-test, and that simply is the process when we compare a sample mean m to a population mean mu when population parameters are known. So we have mu and the standard deviation of the population. And again, our z equation was simply taking the mean difference and dividing by the standard error. And again, standard error was equal to standard deviation of the population over square root of n. And the way that Chapter 9 was different, so we referred to Chapter 9 as a single sample t-test. And in that process, we compare a sample mean, m, to a population mean, mu, when the population standard deviation is not known. So again, it differs from the z-test because we don't have access to all the population parameters. In particular, we would have the population mean, but we would not have the standard deviation of the population, so we would have to estimate that. And we learned that our T-statistic was equal to m minus mu over the estimated standard error. And estimated standard error of the mean was equal to standard deviation of the sample over the square root of n, or the sample variance over n, and we take the square root. So again, the reason why we would opt to conduct a single sample t-test, which is the comparison of a sample mean to a population mean, is because we would not have access to all the necessary population parameters. Again, in both of these instances, what we want to find out is the sample significantly different than the population? And it could be that we are administering treatment to the sample and comparing it to the untreated population. Whatever the scenario is, again, the purpose of calculating the z-statistic or the t-statistic is to find out if that value is different enough from the population value that we're comparing it to, if it's different enough where we would say it's due to treatment or due to the difference in the quasi-independent variable. So now in chapter 10, what differs is the process and also the equation. But before I move on, I just want to note again, this is chapter 8, and this was chapter 9. So in chapter 10, we're discussing t-test for 2 independent samples. And the process that we're engaging in is as follows. We compare sample 1 at mean. So we would have mean sub 1 to sample 2 mean. So mean sub 2. And the reason, the difference, instead of comparing it to population, is the reality is that most research is conducted by taking samples from populations and comparing those samples, which are representations of the populations. It's rare to have population parameters. We may have the mean, but we don't have standard deviation. In that case, we can engage in a single sample t-test. But most cases, the populations that we're interested in, for example, we're testing out a new antidepressant drug. We want to know how effective the drug is. So we may not have access, we probably don't have access to all those who suffer from depression. That would make up the population. And we certainly can't test everybody. We can't administer the treatment to everyone in the population. So therefore, we would take population 1, right? We would take a sample, and so let's say this is untreated population, and then the treated population. Again, we're going to select a sample and average how much depression they're experiencing, and they then represent the treated population. So again, we're taking 2 samples and now comparing one to the other. Note the difference of what we did in the previous 2 hypothesis tests. Those tests compared 1 sample to a population, and now we're moving into the process of comparing sample to sample. And each sample is a representation of its larger population. So again, we would technically take this sample here, right, from this group originally, right, because we take those who are suffering from depression, we select a sample, and then we administer treatment. And once they receive treatment, then they represent the treated population. But for purposes of just simplifying what we're doing, we're comparing one sample to the other. And again, don't lose sight of the fact that each sample represents a larger population. And we have new T-statistic, or we calculate T-statistic, but the equation is a little different. You can think of chapter 10 as a process of doubling everything we did in chapter 9. Chapter 9 was a single sample t-test. Chapter 10 is a test for between 2 independent samples, and this concept of independent samples comes from the way that we allocate participants into these two groups. The word independent means that we have a separate group individuals in this group, and we have a whole other set of individuals in this group. So they're different people. They're independent of one another. And we sometimes refer to that as between subject design. And again, that means participants in each sample are different. So they're different people. And this is important because chapter 9 is the process of comparing two samples, but it's the same individuals. So they are exposed to one condition and then they go into the second condition. We recycle those participants. In this case, they're independent of one another. They're separate. So this would be ideal for something like comparing males to females or social majors to psych majors. Notice that, again, they're made up of different individuals. In chapter 11, when we refer to it as a repeat measures t-test, we're using the same individuals and exposing them to the different conditions. So they get treatment 1 and then perhaps treatment 2, and then we assess how they did. So that would be ideal for something like a before and after trial. How did they do before they got the treatment, and then how did they do after? Notice it would have to be the same people, same individuals, same participants, same subjects in the different groups. Before I speak any more about chapter 11, let me go back to what we are discussing here. Again, this is pertinent to chapter 10. So our equation for our t-statistic is as follows. So our new t-statistic is t is equal to, again, we're looking at the mean difference between two samples. So sample 1 minus sample 2, and then we take population 1 minus population 2, and I'll speak more to that in just a second. And then it's over what we refer to as the estimated standard error of the mean difference, but pertinent to this independent measures t-test. So it's notated in this manner. So S, and then in parentheses, M sub 1 minus M sub 2. Again, in chapter 9, our t looked like this. Our t equation was M minus mu over S sub M. So notice the similarities, but just as I indicated previously, it's almost as if we're doubling everything. So the information here comes from sample data. So we're going to have the ability to calculate the average for sample 1 and then average for sample 2. And then this information represents the null hypothesis. What does the null say? The null says no difference. And so what we're saying here is that the difference between the samples minus the difference between the population, given what the null states, the null indicates no change, no difference between these groups. Then if that is true, we would assume that this is the case. It always equals 0. There's no difference between the two. So in our equations, that portion of the numerator of this equation is always equal to 0. However, I don't want you to omit it from the equation. That would be improper. Just because it always equals 0 doesn't mean that you delete it from the equation. Make sure you're always including it because it draws attention to what we're comparing. And again, we want to see if there's a difference between sample 1 and sample 2, calculate that difference, and see if it deviates from the anticipated population mean difference. Again, in the center, the null is always in the center, which says that there is no difference between these groups. So this is what we are saying, the population 1 minus population 2 mean. No difference means that that would equal 0. And we want to find out, is our sample mean minus sample mean 1 minus sample mean 2, hopefully out in the tail, right? We're going to calculate a difference there. Or does it reside really close to the mean difference between populations? So again, notice the difference. Now we're shifting from just calculating a t-value for one sample mean. We're now calculating the t-value for the difference between the two sample means. And again, so it's still, the wording of the numerator is still the same, mean difference. But now because we're working with sample to sample, it's as if we're doubling everything. And then the denominator is the estimated standard error of the mean. Estimated standard error of the mean. And this is referred to as the estimated standard error of the mean difference. So the key word in this chapter is the difference, because we're looking at one minus the other. So when we talk about the standard error back in chapter 8 was the average difference between the sample mean, m, and mu. In chapter 9 it was the estimated standard error, which represented the estimated standard error or difference between m and mu again. But now in this chapter it represents the average difference that we would expect between these two sample mean differences and the null, or these two and the null, or we may have another sample difference over here. So notice that they're not all equal to 0, and the estimated standard error of the mean difference is the average mean difference between samples compared to the average mean difference of the population, which again comes from the null and is always equal to 0. And as you start to learn these equations and the concepts of chapter 10, I highly recommend that you review the detailed learning objectives that I've posted on Blackboard. It gives you more verbiage as to the differences in the variables in this chapter in comparison to the previous two chapters, and I think it helps clarify what these new variables represent. And again, I can't stress enough that the key word in this chapter is the mean difference, or difference between two groups that are independent of one another. So much of what I've already presented will appear in the subsequent slides, but I felt it was important to review kind of where we were, where we've been, and what we've learned, and preface all of the chapter 10 material with a brief summary of what the z-test looks like, single sample t-test, and how that's different from what we're doing in this chapter. So again, chapter 10, the independent measures design, refers to the process of what most research looks like. So it compares two or more sets of data. Again, it could be multiple means. We could have sample 1 compared to sample 2 and sample 3. We can have a multiple number of samples. For purposes of simplifying things, we'll be focusing on just two samples. So again, data from two completely different independent participant groups, which is referred to as independent measures or between subject design, is utilized. Data from the same or related participant groups within subject design or repeat measures design is referred to the process of a t-test for repeat measures, and this is chapter 11. Okay, so this is pertinent to chapter 10. So here we're just introducing the two different ways in which we can compare sample to sample. So in chapter 10, those samples are made up of different individuals. In chapter 11, we're comparing sample to sample, but they're made up of the same individuals. And you must be conscientious that these things are interchangeable. The concept of independent measures and between subject design, those are synonymous with one another. Within subject design is synonymous with the process that we refer to as repeat measures. So again, I'll use those interchangeably, so make sure you understand which goes with which. Independent means they're between subjects, and then within is repeat, same individuals. So again, here, different individuals in samples. In this process, same individuals. In samples. So we recycle them, we expose them to all the different conditions of the independent variable. So as you can imagine, the computational process for those two different tests, the independent measures and the repeat measures tests, are different, and I've already introduced the basic structure for the t-test for this chapter. Each design has different strengths and weaknesses that I'll discuss later. And because they do differ significantly, we assign the different types of tests to different chapters. So again, chapter 10 is the independent measures t-test, and in chapter 11 we will learn all the ins and outs of the repeat measures or within subject design. So figure 10.1 is a good visual illustration of what we are engaging in with the independent measures t-test. So let's say we're interested in determining what type of teaching method is most effective with students. So we may find that when we're teaching math, some mathematicians or math teachers may feel that rote memorization, so the repetition of, let's say, like multiplication tables, is necessary to understand and master multiplication. And another camp of math instructors thinks that conceptualizing this idea of multiplication is necessary to master that skill. So we want to test which method of teaching math is more effective. So we could say rote memorization versus conceptual learning. And obviously we're not going to have access to all individuals learning multiplication tables. So we take a sample of students and we expose them to the rote memorization, let's say for 10 weeks. And then we have another different group of students, and they're taught the multiplication tables by conceptual learning, and recognizing that we're using those samples as a way of inferring what the populations would look like if we were able to teach math in either fashion to the entire population. So again, we take samples from the populations, we expose them to these different treatment conditions, and given how they perform, we then draw conclusions about what the populations would look like. And for us to determine if there's a difference, again, we're going to determine what the average is here for sample A. And sometimes I'll write the sub notation based on what we're talking about, or I may just write sub 1 or sub 2 to differentiate the different samples. And so sample 1 compared to sample 2, we want to see if they're statistically significantly different from one another when we take the mean difference. And then if there is, then we could say something about the populations that they represent. And again, we're hoping to reject the idea that the null states that population 1 minus population 2 is equal to 0, that they would not be different from each other, and they would produce the same result in this case, on a math standardized test. So in the family of t-tests, it will follow that same four-step process that we learned back in chapter 8, where we state the hypothesis, we set our criteria, collect data, draw our conclusion. So as long as we understand that logical four-step process, we can learn the new elements of these new t-tests, but follow that same procedure. And again, we always begin with the research and null hypothesis, and the notation is a little different, again, because we're comparing the mean difference, again, the keyword difference, opposed to just the sample compared to the population. We're comparing sample 1 minus sample 2. So one way to express the null, again, the null says no difference between the populations. So again, null states no difference between populations. Population means, I should say. And this is one way of stating the notation for the null. It says population 1 minus population 2 is equal to 0, which is also the same as saying if we take population 1 average and it's equal to population 2, right? If you take one thing and subtract the other and they're equal to one another, then the difference would equal 0. So we can also write it in this form, that population 1 is equal to population 2 because there's no difference. At least that's what the null states. The alternative hypothesis for the independent measures t-test, and again, this is for non-directional. This is not specifying a direction in which we expect that mean difference to be. We're just saying that it will be different or will not be different. Here, we are indicating that there is a mean difference. And we can state it in this format where we would say population 1 minus population 2 does not equal 0, meaning that they're not equal to one another. Or we could simply say population 1 is not the same as population 2, that they differ. So again, these are the two variations as to which we would see a non-directional hypothesis and alternative hypothesis written and expressed. So here, as presented earlier, this is the basic structure for the t-test for independent measures. So t is equal to, and again, m sub 1 minus m sub 2. That's coming from sample data that will either be given or we compute given x values. Don't forget how to calculate the average of a sample. The average of a sample is the sum of x over n. So we may be given x values and need to produce the sample mean, or we're given the actual mean already computed. And then the second part here, this represents the null. And always equals 0. Okay, so we know that we're talking about the difference between the sample statistics that we're collecting and comparing, and then subtracting the representation of the null that says there's no difference. And then the denominator is the estimated standard error of the mean difference. I always include that additional verbiage so that you understand why we see this part in the notation. So the estimated standard error of the mean difference. The estimated standard error is a measure of standard or average difference between sample statistic M1 minus M2 and the population parameter mu1 minus mu2. So again, we've learned what standard deviation was. Standard deviation is the average difference between x values and the mean of a distribution. We learned what the standard error was equal to. Standard error was the average difference between a sample mean and population mean. Estimated standard error was based on using sample statistics to, again, assess the average difference between a sample mean and population mean. And now this estimated standard error of the mean difference is the average difference between sample 1 minus sample 2 compared to mu1 minus mu2. So it gives us a sense of how much difference is reasonable to expect between two sample means if the null hypothesis is true. And one way to compute the estimated standard error of the mean difference is shown here. And I will caution you that this is not the equation that we will be using, but this is a good starting point given what we learned in Chapter 9. And I'll explain more as to why we will not use this equation on a regular basis in this chapter. Remember that I said in Chapter 9, again, it was a single sample t-test. One sample was being compared, and now we have two. And I said you can think of this chapter as a way of doubling everything. So in Chapter 9, our estimated standard error of the mean was equal to our variance, if we were using variance, over n, and we took the square root. Notice that that is this part of the equation, and we double it because we have now two samples. So again, this was for chapter 9, estimated standard error, and this is now referred to estimated standard error of the mean difference. And so we're talking about the inclusion of two different samples. And now I'll explain the reason why we won't utilize this equation is because this equation is only mathematically correct if our sample sizes are equal. So those individuals who don't get the drug, we have 25 of those. And then in sample 2, those who get the drug, we have 25. Well, it's unlikely that when you're conducting research, you will always have an equal number of participants in the different conditions or categories. People's lives change, they drop out of studies, you may not be able to recruit enough individuals to have equal number of sample sizes. So it's unlikely that you would have equal sample sizes, and therefore this equation mathematically would not be appropriate because having more individuals in one group will weight those values one way or the other. So again, we start with this equation just to show the similarities between what we learned in chapter 9, but we recognize that it's not going to be as efficient in cases, or applicable, I should say, in cases where the sample sizes are unequal. So let's say, for instance, we had one sample that, due to certain life circumstances, then became 18. And as a consequence of that, then mathematically this would not be a fair computation for producing the estimated standard error of the mean difference. I will present the alternative equation, which requires us to calculate what we refer to as the pooled variance, taking the variation of both and pulling it together, which allows us to account for differences in sample sizes. So pooled variance, equation 10.1, which was just presented, shows standard the error concept, but is unbiased only if n sub 1 is equal to n sub 2, just as I just indicated. If the sample sizes are equal, then that equation is sufficient. But instead of always having to pay attention to the fact that whether or not our samples are equal, it's preferred just to utilize this new equation referred to as pooled variance, and accounts for the variation in both samples and takes into account the differences in sample sizes. So our pooled variance, the notation is S, so variance, again, always S squared is always representative of variance. And this little p-value means that it's pooled. And our equation is SS 1, so the sum of square deviations for our first distribution added to SS for our second distribution, and then divided by the sum of the degrees of freedom. Now let's think back to what variance looks like just for one single sample. Variance is equal to SS over degrees of freedom. So again, notice that we're just doubling everything because we have two different samples. So this equation shouldn't look as scary or overwhelming as it initially appears. Again, don't lose sight of the fact that the sub numbers are just a label. This is sample 1, sample 2 statistic, sample 1, sample 2 statistic. So again, going back to when we just have one sample, this is what the variance equation would look like. Now, let's not forget the SS, sum of square deviations, which was presented back in chapter 4, and we will need in this chapter, could be computed one of two ways, using the definitional formula, so the sum of our mean deviations squared, or we could utilize the computational formula, which says we take the sum of all x values that have been squared, subtract the sum of x squared over n. So again, this is from chapter 4, but we're going to need that to compute these values. In some cases, those values may be givens, but we shouldn't lose sight of how they were computed in the first place. Next, I want to present an alternative equation for pooled variance. So you will utilize both you'll get the same answer if you use one or the other, just as in the case of calculating the sum of squared deviations. So the alternative equation is for pooled variance. So again, variance is always s squared. The subnotation of p just means pooled, is equal to the degrees of freedom for our first sample multiplied by the variance of our first sample added to the degrees of freedom for a second distribution multiplied by the variance of our second distribution over, once we take the summation of those two products, over the degrees of freedom for our first distribution added to the degrees of freedom for our second distribution. And some of you may be completely overwhelmed and your eyes have now rolled into the back of your head. Don't be alarmed. This equation isn't as scary as it looks. And in fact, if we look at what variance is equal to, variance is equal to SS over degrees of freedom. If we're just talking about one single sample. And again, we see that here, right? It just doubled. Now, what would be a way of rearranging this equation so that I solve for SS? In other words, in this numerator of this second equation here, how would I express SS? Well, if I just use simple algebra, I would say we multiply by degrees of freedom here, degrees of freedom here. Now I can say that SS is the same as degrees of freedom multiplied by variance. So all we've done is rearrange the variables and substituted SS for the equivalent, which is the product of degrees of freedom multiplied by variance. So again, the equation isn't as scary as it appears, and all we've done is moved variables around. So instead of taking the sum of squared deviations for each separate sample, I'm expressing SS as the product of the degrees of freedom multiplied by variance. So hopefully you can see how these variables are related to one another. And it is also my hope that it demystifies these equations and simplifies them for you, where you're not overwhelmed by all the letters and numbers and subnotation. Again, students tend to get a little overwhelmed, but if you break it down one variable at a time, it's pretty basic and straightforward. So now we can use our pooled variance to calculate our estimated standard error of the mean difference. So here's our equation. Our S sub M1 minus M2 is equal to the square root of, we have pooled variance over N1 added to the pooled variance over N2. For a moment, let's refer back to what we learned in chapter 9. We learned the estimated standard error of the mean was equal to the variance over degrees of freedom, and we took the square root. And so notice now the similarities. Again, it's as if we're taking this and doubling it because we have two different samples. And we are dividing by n instead of degrees of freedom. And excuse me for my error, just what I said was not corresponding to what was happening in my head. So this should not be degrees of freedom. I apologize. That's our equation for variance. This would be n. And that's why, again, we see that this, right, is the same as here for my first sample. And because we have two samples, I do it twice. But instead of just variance alone, it's now pooled variance, because pooled variance is accounting for the variability between the two samples, accounting for the fact that most likely those sample sizes are not equal. The size of those samples are most likely unequal, and the pooled variance accounts for that or takes that into consideration. So again, this is chapter 9, estimated standard error of the mean. And now we have estimated standard error of the mean difference, right? The keyword difference. And it's calculated by taking these two fractions, adding them together and taking the square root. And that's important to focus on for a moment here. this equation is not equal to this, which is a very common mistake students make. And most likely this mistake is made because of the equation we just presented for pooled variance. But these two things are not equal to one another. This line, right, this division does not go all the way through, and these are consider these as two separate fractions that need to be summed together, and then we take that summation and take the square root. Here we're taking the sum of the pooled variance, adding them together, and then dividing by the sum of sample size. Again, this is a very common mathematical mistake. Do not do this. If you do, you will produce the incorrect answer. And again, I think the reason that students make that mistake is because one of the equations for pooled variance is as follows, is SS1 added to SS2 over degrees of freedom 1 plus degrees of freedom 2. So once we've used this one, this is one fraction, right? And students tend to use that structure and then compute estimate standard error of the mean, but do so incorrectly when they use that same structure as if it's one fraction. We have two different values here, one fraction here and one fraction there. So please don't make that mathematical error. And so before I move on, I want to visually express again what the estimate standard error of the mean difference is representative of. So if we have our distribution, the null will say that population 1 minus population 2 is equal to 0. And let's say we take sample 1 minus sample 2, and it doesn't equal 0. Let's say it equals 2, the mean difference between those two. And let's say I take another set of samples, and I'm just going to sub-number them accordingly. So sample 3 minus sample 4, and that's equal to, let's say, 5. And then I have sample 6 minus sample 7, and that's equal to 3, let's say. And just to simplify, they're all on the positive side of the distribution. But again, we note that the difference between these samples don't all equal 0. And so from the difference from 5 to 0 is 5 points, from 3 to 0 is 3 points, from 2 to 0. And so what this represents is the average difference. So each one deviates a certain amount. One sample mean minus the other differs by 5 points, and in comparison to 0, it differs 5 points. The next one, 3 points and 2 points. So again, it's the average difference between all these sample mean differences and the population mean difference that's coming from the null. In chapters 8 and 9, it was standard error was the difference between sample 1, 2, again, this is all theoretically, how many samples we may produce in a distribution of sample means. And again, when it was standard error, we were just expressing on average how much these sample means deviate from the population mean. Now notice the difference. We're not just talking about the sample, we're talking about the sample minus the other sample, so the mean difference. Hopefully this visual gives you a better sense of what we're calculating. It's essential to not understand how to calculate it, but understand the definition and what it represents. Okay, so really quick, again, we're going to follow the 4-step process or procedure for conducting a hypothesis test, which requires us to compute a T-statistic. So we've just gone over the variables of our T, and I just want to review that. So our T is equal to sample 1 mean minus sample 2 mean minus population 1 mean minus population 2 mean, again that always is equal to 0, over the estimated standard error of the mean difference, and we just learned that that's equal to the estimated standard error of the mean difference is equal to the pooled variance over n, and we take the summation of those two fractions and then take the square root. And we also learned that pooled variance is equal to sum of square deviations for our first distribution added to sum of square deviations for our second distribution over degrees of freedom for our first plus degrees of freedom for our second distribution. Or our alternative equation is pooled variance is equal to degrees of freedom for our first distribution multiplied by the variance of our first distribution added to degrees of freedom for our second distribution multiplied by the variance of our second distribution over degrees of freedom 1 added to degrees of freedom 2. So these equations we just went over. Again, the beginning values are T-statistic. The second equation is estimated standard error of the mean difference. And the third is pooled variance. And in order for us to find the critical t, we need to know degrees of freedom to enter that t-table. So now I'd like to discuss how to calculate degrees of freedom for a t-test of independent measures. So degrees of freedom for this chapter, from chapter 9, our degrees of freedom is equal to n minus 1 when we're only working with one sample. And now we're working with 2. So when we're finding our degrees of freedom to identify the critical t, we're going to compute degrees of freedom in the following manner. Because everything's doubled, essentially we're saying degrees of freedom for this chapter is equal to n sample 1 minus 1 added to sample 2 minus 1. Again, we're just doubling what we saw in chapter 9. So again, it's the difference, n minus 1, twice for us to be able to find degrees of freedom, which is needed to find our critical t. And here, just note that this term is the same as the denominator of the pooled variance, which I just presented, and we see that. Again, the degrees of freedom for our first distribution is the same as n minus 1, and degrees of freedom for our second is n2 minus 1. In the next chapter, we'll actually go in more depth of conducting a hypothesis test using two sample means and discuss more about variability and the assumptions that pertain to this type of hypothesis test.